we're going to be doing quite a few clickers here, clicker questions in just a minute. So get your clickers out, and we'll get you going on that. Now remember, the clicker questions until I guess January. What's today? The 19th. Until next Thursday, the 26th. The clicker questions are practice questions. But today they're going to be all, there's no Chuck Norris type questions. It's all concept questions. And we have all multiple choice. Next week I'll probably show you how to use clickers to input numbers and stuff. It's pretty easy. But we got a bunch of them today. But if you remember, if you get one of these wrong during this period of time, it's all right. When January 31st arrives and we officially start taking clicker data for your semester grade, even then your participation is what's required. Now, you might want to start your notes today with a little announcement from me, specifically about bonus points. It's not in the syllabus, but it is something that I traditionally do every semester. And that is for students who answer 75% of the clicking questions in class correctly, I give 4 bonus points at the end of the semester. Okay? And so you can think of that as an extra 4 points on your final exam. All right, but you won't know whether you get them until the end of the semester. Okay, so you have to get 75 of them correct. Now, for the regular 25 points out of 25, or maybe fewer than that, for the semester grade, this is a regular pointage, not bonus pointage. Those are based on 85% that you click, whether correctly or incorrectly. All right, so the clicking that we're going to do on January 31st for regular 25 out of 25 on your semester grade, it will go in based on your participation, whether you clicked on a given question. The bonus pointage at the end of the semester is based on how many you get correct. So when you're in class, don't just, A, and I see somebody in the back laughing. I guess that was the strategy for some people. But what you want to do is answer as correctly as you know, because then you'll be able to snag 4 bonus points. And believe me, 4 bonus points out of 250. So adding to the numerator of your final percentage for the semester, 4 points out of 250, it's more than 1%. So it's a nice little chunk of change. And you get those points if you answer 75% correctly. So that's like getting a B on in-class clicker questions. I mean, if you take all 97 or however many we eventually ask, and you get 75% of them, and if you think of those all as one big test, that would be like getting a B. And if you get a B on the clicker questions in class, 75% correct or more, then you get 4 bonus points. All right, so traditionally I do that. So definitely, when we get to the clicker questions today, you definitely want to try to answer them as correctly as you know how. Another thing I want to mention to you, the SI schedule, it's apparently they've got it set up for Monday, Thursday, and Friday, and I don't like the schedule, and I didn't complain, but I asked the SARC people, see maybe if you can get another, you and Maria can coordinate on maybe getting a Tuesday or a Wednesday session. And so I'm putting up TBA. Now, are you going to have a session today? if it's on the schedule, is you have a Thursday session, right? The Thursdays, there's nothing wrong with the Thursday sessions or Friday. We just want to have something on a Tuesday or Wednesday so you can talk about Tuesday lecture. That's all. Anyways, when is your session today? 1:30 today. And where is it located? Engineering Building 1, room 383. So when you go over there, try not to try not to disturb the engineering majors. They're a little squirrely most of the time, so I mean mentally. So question. Supposedly, and let's just go with that for today, and I don't think they're going to change it, but I'm not going to announce it till I've absolutely positively assured myself that they cannot change it. But for today, yeah, 1:30, room 383. And keep an eye on, not announcements, but discussions, and I'll announce the rest of the schedule in discussions. All right. They'll probably get back to me today about any changes. But for right now, it looks like Monday, Thursday, and Friday. And what is it, 2 sessions on Monday? Yeah, so. Anyways, now, let's get down to business. Let's do a little recap on what we studied last time. We looked at the graphs of motion and analyzed them, 2 different kinds. One was the graph of position over time, and the one that the version that we chose to study was like a strobe diagram or a set of strobe photos. For instance, like this little diagram of a car, snapshots taken, 4 snapshots taken, and viewable in the same view. And this is kind of an idealized view, but we can still, if we think of this as equal elapsed time, delta t, between each image, then yeah, we can use that to analyze the motion. And I would like to start with an iClicker question about this one. So kind of sketch in this diagram, and I would suggest that you make the clicker questions today part of your notes. All right, because we're going to be talking about them. We got a whole bundle of them, and we have a lot to talk. There's going to be a lot to talk about. All right, so here we go. Clicker question number 1. Oh, by the way, if you're using your clicker for the first time, hold the power button down until the big rectangle flashes, and then type in the letters BB, and that'll get you synchronized to the session. Then you'll get a Go Nitro message, and then ready. Who's got ready? Okay, good. Who doesn't have? Who's got no base? Anybody got no base? All right, let's keep going. Here's your question. Number 1. In this simulated strobe photo, cars moving left or right. So in other words, it's not backing up from right to left. Okay, go ahead and answer that. And thank God there's no flickering in the screen today.
Yeah, I don't think it had flickering when we used the HDMI.
Yeah. We're using the HDMI cable, so hopefully this works a little bit better for you guys. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead. Let me see the. All right. Okay, you guys did really good. Correct answer is, yeah, it's moving rightward and it's speeding up. side note or addition to your notes for this diagram. How do you visually recognize or spot that it's speeding up? Because the distance between strobe flashes is getting bigger. It's kind of pokey over here. It only goes a few meters over here between flashes, 0.2 seconds. But over here, in between the third and the fourth flash, you're really booking. Right? So that means it's speeding up. Covered a lot more ground in 0.2 seconds. All right. Another thing that we talked about last time was the velocity graph, the graph of velocity versus time. And here's one of them. And go ahead and make a sketch of this. Just to remind you, this one, I've labeled the vertical axis v subscript x. And what that means is that this is the horizontal component of the velocity. So if you have something that's arcing upward and to the right, it's going to have some Vx, V subscript x. And because it's moving upward, it's going to have some V subscript y. So this is a chart of the V subscript x part of the motion, the horizontal part of the motion. And it's got a red, the graph itself is the red kind of fuzzy line. And the plus or minus, don't forget, on this means positive Vx. In other words, rightward. Normally the positive part of the x-axis is rightward. And the negative part, and so the Vx is also the same. So a positive Vx means rightward motion. Negative Vx means leftward motion. All right? Now make sure you make a note of that because you're going to have to interpret the meaning of this graph. And don't forget, there's all kinds of meanings in here. In other words, the width of the graph, it's run in terms of rise over run. Hopefully you remember that from high school geometry class. The run has a definite meaning. So does the height of the graph. It's rise, or in this case, it's dip. It's dipping downwards to the right. That has a meaning, all right? And we're going to be talking about that. The slope, the rise over the run. In other words, the ratio of rise over run. Yeah, that has a meaning as well. And we're going to be talking about that in just a minute. Matter of fact, the polygon that the red velocity graph forms with the time axis, or the set of polygons, has a physical meaning. They all have a physical meaning. And that's one of the things that we were talking about in class last time. Now, let me go and try some more iClicker questions with you and make a good sketch of this graph for your notes. And you're going to want to make sure it's a big sketch so you can add notes to it, because we want to think about the meaning of this graph. And this is a visual graph, and so what we're doing is visual thinking, but then we want to transfer it into verbal thinking, in other words, sentences, all right, and write those in your notebook. All right, so let's get to that. And I had this little blurb here, frequency BB. Should have been on the first clicker question. Anyways, clicker question 2. The full graph shows what? Is that your clicker with the Cubs hat? Yeah. How come she had it? Oh, okay. I was just trying to work out, why, if they're friends, why are they sitting, maybe she's sitting behind you to keep an eye on you and stuff like that. I don't know. I'm not trying to say nothing, but anyway. All right. Let's see. So we're getting the answer. So look at that. That's interesting. Think. Which of these 5? "20 seconds. I want you to think, but we do have stuff to do, so I don't want you to think for 30 minutes about it. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ding. All right, toggle to computer. Now look at what we got here. One person thought it's searching for Waldo. Well, it is a practice day, so I guess I'm not going to give you the business. But definitely look at this. We have a definite spread, a distribution of answers. And what that tells me is your thinking is distributed over a set of various ideas. But only one of them, the previous question, is just one big stack. I think it was like 97% for question 1. But this one, we've got a smorgasbord of thinking about it, so we want to talk about it. All right. Now the answer, go ahead and swap back, is not D. The answer is C. Now let's think about this. All right. Now add this to your notes and add this to your diagram. Okay. Up here, the graph is above the time axis. So that means it's 2 meters per second and so forth. That means it's moving rightward. All right? And that's the initial state is 2 meters per second, and then it goes to, it slows down a little bit. Okay? Down here, in the lower half, the velocity gives a negative number. And that means that for the second half of the motion, it's actually traveling to the left. All right? And in between there, it has a turning point. It comes to a stop right here at time t equals 1 second. So make a note of it. We've got option C, and all of that is interpretable from the overall shape, the axes, and the graph itself for this object. All right? Now, we want to be able to look at that because it has physical meaning. Remember, we're trying to make true sentences, true statements, true claims about the physical universe. And we want to think about it mathematically. And in this case, we're going to think about it visually so that we can get to some formulas, because we know in Professor Galileo's viewpoint, everything that we say physically about the universe is going to have a mathematical nature at some level. Whether we can state it in this class or not. There's a lot of stuff, like sunspots in the surface of the sun. Extremely complicated calculus for that. It would even cause me to choke. Okay? There's a lot of stuff that we won't go over, but everything that we do go over in this class, there's going to be a mathematical content to it. All right, let's go to the next question. Okay, question 3, the run of the graph. 2 seconds. Okay, and here's the run. I sketched it in there. All right. So in terms of rise over run, that's the horizontal extent of the actual red graph. What's the meaning of that? "30 seconds. Uh, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay? Toggle to the display. All right. Now there's a big pile of you that have piled up for option C. But there's a few of you that are over here with option A and B, and one person for option D. Now, go back to laptop. This is going great. Very happy about it. The actual answer is that's the duration of the motion. Now, why is that? Well, it is the extent of the graph along the temporal axis, the time axis. So we would use the word duration for that, or maybe elapsed time, you could call it that as well. And that would be synonymous. Okay? All right? It's not the object's acceleration, and that would be, a different quantity maybe. The distance traveled, we know how to interpret that from one of these graphs, so that's not the distance, and it's not the object's delta V. All right, and nobody voted for E. All right, good. Question 3, or question 4. The rise. Here's the rise. Over here in blue. And I kind of penciled in a little dotted line there for you. So add that to your notes. The rise. Now, the word rise is what you'd use in geometry class, and it would be perfectly kosher to do that. But in this class, we interpret that geometric concept in a physical way. All right? Now, it's not the mass. It's not the temperature. It's not the density, but it is something in this set of options A, B, C, D, and E. Okay, 20 seconds. What about it?
Do you see a pen under my chair?
No. You can get up. Do you want to borrow one? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Toggle to this to computer. All right, now we got to rate. All 3 of you voted for C. Now that can't be the same as the previous answer. So you caught yourself napping on that one. But the rest of you, most of you, have a distribution of answers here. So let's clear it up. Okay, the answer, can you click back to the laptop now? Okay. The answer is, that's actually the delta V. That's the change in the velocity. He goes from positive 2 meters per second to negative 2 meters per second. All right, so that's a delta V. It's not, and if you remember anything from Tuesday class, you know that is not the distance. And it's not the run. And students, the acceleration, well, we'll get to the acceleration in just a second here. Matter of fact, let's keep going with the questions and we'll get to it. I don't know which question this is, number 5? Yeah, okay. Question 5, rise over run. What's the meaning of that? It's negative 2. It's the ratio of delta V over delta T. The run was 2 seconds. The rise was a dip of 4 meters per second. So this is a negative 2 meters per second for the slope. What does that mean? Looking good. $20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ding. All right, go ahead. Yeah, go ahead and show that. All right, we got a little bit of an argument between A and B. Toggle to laptop, please. And the reason for that is rise over run geometrically for this diagram, for this graph, it's delta V over delta T. All right? And that's the definition of acceleration. So make a note of it. The slope of the velocity graph, whatever it happens to be, this is a negative 2 meter per second, that's the acceleration of the object. And notice that if you have a horizontal graph, constant velocity. Now, constant velocity means no acceleration. Speed's not changing. And a horizontal line segment means that you have a run, but you don't have any rise. So rise over run is 0 over whatever the run is. That's 0 slope. Okay? So the slope in this graph is interpretable as the acceleration. Make a note of that. Okay? Now let's think about this object. Let's think about it some more. It slows down from positive 2 meters per second, then it stops at t equals 1 second. But just for that one instant of time, because then it starts acquiring negative velocity, i.e. leftward velocity. Okay? So it's a turning point in the motion. It reverses field. It's like walking forwards and then walking backwards, backing up. And we do that all the time, Next question. Boy, I'm loading you guys with questions today. Good. What is the area of the first distance triangle? Now I want you to shade it in. Okay, so the first distance triangle is this one, right here. Go ahead and shade that in. All right. And then answer this question. What's the area of that? I'll give you a second to do it. It's not too cinchy. You can do it in your head if you think about it carefully. Or you can use your calculator. Take you just a little bit longer. Who remembers the formula for the area of a triangle? What is it? What? Right, 1/2 base times height. All right, so that's what you want to use here if you dare. 30 seconds. You're doing good. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And you can see we have a spread of answers here. Now let's get down to business. It seems like we got a little bit of disagreement. So let's go to the basic formula. And this is the geometric version of it. 1/2 base times height. So if you have a triangle, 1/2 base times height, always. All right. In this case, the 1/2, I write that down as a 0.5. The base is 1 second. Now that's just for this shaded in triangle here. That's all I'm focused on right now. This other one we could deal with that later. All right. But for this one, it's just 1.0 seconds, and that's the base. Now the height is 2 meters per second, 2.0. All right? And so those multiply out to 1 meter. And don't forget, this seconds in the denominator of the quantity 2.0 meters per second, and the second in the numerator of this 1.0 seconds, they cancel. All right? And you're left with meters. All right? And in English, you would describe this mathematical statement as the distance traveled by this object on its way to the right. All right? Because that first half of the motion, it's got a positive velocity, so it's heading over this way. All right? Now the second half of the motion, there's your answer, 1 meter, option C, which most of you got, 69%. That's good. And this, my last comment to you is we started up here with a geometric interpretation, and last time we connected that to this formula, this dynamical formula, you could say, distance 1/2 AT squared. All right? And we worked on that problem as well. Now, I want to make a spatial map from this same information. All right? And so let's do a little bit more notes. Let's make a spatial map. Now, we know it's moved 1.0 meters rightward in that first 1.0 seconds. All right? And the starting point, let's just call the starting point x equals 0.0 meters. And let's say that the starting point is the starting time is 0 on the stopwatch. All right? And so you have, here on the left, at position 0.0 meter, and up here the notation t equals 0.0 seconds. And down here, 1 meter to the right, and just, I made it 200 pixels on my screen. No, 400 pixels on the screen. You make it whatever looks good to you. It's the only line segment that you got to do, so you can make it anything on your notes. And that's 1.0 meters. And this, this is supposed to be a yellow hexagon. It looks kind of greenish. To me, anyway. Does that look yellow to you guys? Because I'm kind of looking at it from the side. Kind of greenish yellow even for you guys? Lime, supposed to be yellow. It's yellow on my computer display. It will be yellow on YouTube, but unfortunately it's not a very nice yellow here. Anyways, that's supposed to be the object. And then here's the original velocity graph. And so this is another graph. This is like a strobe, only 2 flashes, so it's no great shakes. But I want to pause here for questions. Make sure you have this sketch down, because we're going to do some more clicker questions here in a second. And I don't want anybody to get caught napping. Now, questions. Okay, let's continue. Another iClicker question. All right, and it's going to be about this pair of graphs, a spatial graph and a velocity graph. And by the way, the spatial graph is something that, I was explaining to a student yesterday in office hours. Yes, we did have some students come for office hours, 9 o'clock to 11 on Wednesdays. And I was explaining, a spatial graph is something that if it's fairly accurate, you could go up into space and make a photograph, like from a satellite or even from an airplane looking down at the Earth and look at the photograph and then look at your map and say, yeah, that's about right. You can compare them. The velocity graph up there on the upper right, no, there's no way to photograph that from space or from an airplane or anything. It's abstract. Okay? This graph down here with the lime green hexagons is spatial, so it theoretically could be photographed. if we actually had the objects in the room. All right. Now, something that I want to point out to you, or I want to interrogate now, is oh my goodness. I have to pause the podcast. Where's my clicker? Okay, here's your brain burner question. And this is question 7. What is the position at time t equals 2.00 seconds? And just for convenience, it might be helpful to darken in this distance triangle over here, just for, because that's the part of the motion that we're concerned about, that particular triangle. Now this one's tough. It requires a lot of thinking, a little bit of calculation, a little bit more thinking, and some decision making. Oh my goodness. Very, very interesting. That is interesting. Very good. Good question. Sometimes my lectures, every once in a while I have a class that is almost all clicker questions. And we just, we learn through clicking and talking. And actually me talking about it and you guys clicking. All right, so let's see what we got here. 75. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Answer. 0.00 seconds. Go ahead to the display. And here's what you guys voted for. Now, option D is the most populated, but it's not a majority. It's only 40%. All right, now let's think about this. Okay. Go back to the display. Thank you. That triangle over there, it's the same size and shape as the other distance triangle. All right, so the area is 1 meter. But it's moving to the left. It's moving to the left from this position right here. From x equals 1.0 meters, it's moving to the left now 1.0 meters. And that puts it right back over here at 0.0 meters. All right? Now, for that reason, I want you to make a note that the area, that if there's area under the time axis, so between the velocity graph, if it dips below the time axis, you sketch in from the velocity graph up to the time axis. That's how you would do it. And that counts as a negative or leftward change of position. So delta x would be negatory. All right? And that, my wonderful students, you can get if you think carefully. And on homework 2, which will activate at 5 p.m. tonight, which will be due on Tuesday next week. For you guys, it'll be due at 10:30 a.m. You'll be looking at some velocity graphs, and I'm not done with it, so I'm going to add 1 or 2 more real brain burners on there for you to think of, and this is going to look like child's play compared to the homework, so, to the brain burner on the homework. All right, so make sure you make a note of this. And when you're doing my homework, when you're doing my exams, remember to read carefully and think. You're going to have to. Because I'm not going to be asking you really cinchy questions the whole time. I expect people in this room to think. And now I want to do some more discussion. And we've been kind of talking about this movie, Hidden Figures. And, you know, I haven't seen it yet. I'm going to try to go see it this weekend, hopefully. But, you know, Hollywood, they mess things up a lot. You know, they jazz stuff up and, you know. But the real people behind Hidden Figures, yeah, I'm going to talk to you about what they do, what they did. And for instance, this lady on the left here, Dorothy Vaughan, she's one of the people. Ah! I just jostled the HDMI cable. Oh! Come on, baby. All right. So Dorothy Vaughan, supposedly she's one of the three women that they wrote this movie about. That's her. That's the real Dorothy Vaughan. And she was, it was kind of interesting. I was reading about her. She first started working for the space. It wasn't a space agency, but she first started working for them in 1943, World War II. So you know what she was probably working on was radar, or maybe sonar. You know, because those are huge amounts of math in those topics as well. But that's her. And she became a Fortran program. Fortran, for those of you that don't know it, is the main scientific programming language for heavy-duty computer programming. NASA uses it. NSA, you know, all kinds of people use it. But banks don't use it. They use a different, you know. And if you took the SAT before coming to college, the Educational Testing Service, yeah, they don't use Fortran. They use a different computer language. But yeah, so she's one of the three ladies, and there she is drinking a Coca-Cola and enjoying a break away from the numbers. All right, so let's talk about Hidden Figures. And what I'm going to show you here today is how they handled it. A spacecraft is not constant velocity, and it's not uniform acceleration either. It's a little trickier, but I'm going to show you what they were doing and how they were able to think the matter through. All right, so let's review what we know. So let's make a verbal report to Professor Galileo. Professor Galileo, here's what we know. I think, yeah. All right. So you can, hold on a second. Go ahead. You can grade it now and then detach this. Eject everything.
Are we going to eject it because we have next class too?
Yeah, because I want to, well, we don't have to eject it, I guess. And then you can grade it. All right, constant velocity graph. Yeah, we know how to handle that. Delta x equals v delta t, or in a little more streamlined version, d equals vt. Yeah, we got that. And the velocity graph for that is a horizontal line segment, which we've mapped out a bunch of times. The distance polygon involved is a rectangle. Cinchy, very easy. Now, an accelerating system is a little trickier because we have something that's not a horizontal velocity graph. All right, so if it's accelerating from rest, or if it had original initial speed and slowed down to a stop, Vf equals 0. Then the formula that we figured out last time was delta x equals 1/2 AT squared, or over here in big letters, D equals 1/2 AT squared. Now that's for very specific that is an accurate formula only if you either stop or you start from rest and attain a final velocity. All right, you use that formula. If you have something different than that, you got to use a little fancier formula. And actually, we're going to work on putting that all together. Velocity graph is a sloped line segment, either sloping up to the right or down to the right. And the concept that we use is the distance triangle. This is the distance triangle related formula. It's basically that. All right. Now, when you compute that, the distance that you get under an acceleration, you then have to say, all right, that's the distance I've gained. But then if I was already at x equals 4.7 meters, you have to add it to that to get your final x coordinate. All right. So we're not really done until we get everything accounted for. But for the distance you cover during an acceleration from rest or during a slowdown to a stop, yeah, this is all you need. Now, hidden figures, this is the question we've got to deal with. And as I've said before, and as is commonly said, down there in Mission Control in Houston, and actually the hidden figures ladies, they were working up at Langley Air Force Base up in Virginia. This is what they've got to deal with. Because a spacecraft, if you think about it, it doesn't accelerate uniformly. And you've seen that. You know, you watch a liftoff on TV or maybe in person. It just kind of moves slowly, but then it really starts to book. And the reason for that is every second that the rocket motor is firing, it's losing mass out the rocket, at the nozzle in the back. So that means the mass of the rocket is getting smaller and smaller, easier and easier to accelerate. So the rocket keeps burning and it pushing with a certain amount of force, but the rocket itself is getting lighter, so it starts to accelerate faster and faster. And so, in other words, you don't have a uniform straight line segment acceleration for something like a spacecraft. All right. So, in other words, what if you have something like this? Go ahead and sketch this in, something curvaceous for your velocity graph. Now, we had a straight line segment, a horizontal one, constant velocity. We had a straight line segment dipped to the right, and we can do one dipped upward to the right if we want. But this one's kind of a little bit of variation, but it's not straight line segments. So what I'm going to do now is go to the document camera, and I'm going to keep the podcast running. Do you have some notebook paper? Great. Darian's borrowing some notebook paper for me to use. And what I'm going to do, okay, that looks great. I'm going to start graphing, and what I'll do is embed this in the podcast before I put it to up to YouTube. Okay, so take notes now, and everything that we have on the document cam, it will be in the YouTube as well. So, if all goes well. So, let me put this over here. All right. Let me see if I can move this. Okay. And all right, let me magnify this a little bit. I can't remember how to magnify it. All right, that's a little bit better. Okay, PSC 1121, section 0001, January 19th, right? Non-uniform acceleration. Okay, in other words, the real story behind Hidden Figures and why it was such a difficult task. All right, let's sketch out what we know. And I won't be doing this ultra precisely, but it'll be pretty good. Time axis. And let's do Vy. Vertical, the up and down velocity. And we know that if we have something at constant velocity, it's, for some amount of time, t1, and here's t equals 0 down here. We know that it corresponds to a horizontal line segment. The distance is this area. And let me draw a dotted line here. And then the left side is the time axis itself. If we have uniform acceleration, it'll look like this. Let's say we start at rest, t equals 0, and we're at rest right here. And let's give it an upward slant, about like that. And there's my time t2. That's the extent of my velocity graph study. This is a uniform acceleration. Rise over run is equal to delta v over delta t, and that's the acceleration. Here's the delta v, and this is for a speed up. And then, of course, here's the corresponding delta t down here. And the slope, the rise over the run, is interpretable as the acceleration. And distance traveled from t equals 0 is the area of this right triangle. I'll put a little right angle symbol there. Okay. And the third variation of that we didn't really do this one yet. The one that we did in class is this next one. Okay. And this one we're going to start up here at like 4 meters per sec. Let me do something different. 22 meters per second. All right. Just for something different. And this one, we slope downward. I'll make this one steeper than the other one. And so it comes to rest over here. In other words, it stops. All right. And let's see. I really wish I had that chair because this is where the chair would be handy. Okay, the rise over the run, same. Rise over the run is delta v over delta t, and it's the acceleration. And in this case, it's negatory because my rise is actually right here. It's a negative. It drops. You have a negative delta v. In other words, you're slowing down. Okay, so negative delta v. But you still have And we'll call this T3 over here, whatever that happens to be. There's your delta T. And this is T equals 0. And the area of this distance triangle, yeah, 1/2 AT squared, 1/2 base times height. Yeah, we got it. Okay. All right, so that's the stuff that we know. We're going to try to get this stuff up here, non-uniform acceleration. All right, now this stuff is not accelerating. And these two are both uniform accelerations. And this one up here is not even accelerating. But we want to get this non-uniform acceleration, so that'll be on page 2. All right. So let me go to page 2. All right. And so this is 2. All right. Now this one, I'm going to draw a pretty big graph. A little bit bigger than the other one. And let's say that this is the y component of the velocity for some rocket that they're trying out up there in Virginia. You know, they do a lot of testing of small rockets up there, and the bigger rockets they test out here and out in California at Vandenberg and stuff like that. But the small ones are up in Virginia. And let me draw in a velocity graph that gets steeper. All right, so make it kind of a little bit straight here, down here, and a little bit steeper out here. All right, and let's just do that. And let's call that 2.0 seconds. All right. And we're going to give that a time. And put a dot up here for your, and this is V of 2. Okay. Now, this is not going to give you a polygon, but we still interpret the area as a distance. So I'm going to write in the word area equals distance, and we'll say that this is t equals 0 here. All right. And now I'm going to shade it in. Now, it's not a right triangle, although it's not too far from a right triangle. And matter of fact, if you want to make a very imprecise estimate of the distance traveled, you would use the triangle formula. So if you're just trying to do, as they say in rocket science, quick and dirty, here's quick and dirty. 1/2 2.0 seconds times whatever V2 is. So let's say that this is 87 meters per second. That's pretty fast. It's 180 miles an hour or something like that. Okay, so we'll put that. Okay. Okay, now this is assuming that we can use a distance triangle. So you make this calculation, 1/2 times 2.0. So this one tells you that if you want to make an imprecise estimate that's really fast, just do a triangle, a big triangle. And this tells you that the distance above ground is 87 meters. All right? But now, if you want to be more precise than that, you've got to do something different. That's going to be too imprecise for NASA because they fly 87,000 miles. You know, so 87 feet, yeah, that's not going to be too bad. Or 87 meters, that's not too bad. But 87,000 miles or more, 870,000 or more, you know, going to Mars, many millions of miles, forget about it. They can't do it, you know. This is okay, but to get really precise, to put that spacecraft where it's supposed to be on Mars and not to miss the hidden figures. Let's try to do another copy of this. This is what the hidden figures ladies do. Time. Let's make another. I'm going to try to copy that. Okay. So it starts out fairly flat and then steepens. .2 seconds. And we're saying that this is 87 meters per second. And that's V of 2. This is the VY axis. Here's 0 down here again. Now, here's what they do. What they do is take a smaller time interval. All right, so I'm going to convert this into, here's 1 second. All right, and let me cut this. There's 1.5. And let me cut 1.1, 1.2, 1.3, 1.4, and 1.5. All right, so here's what they do. The hidden figures method is to compute the area of each of these little polygons. Many narrow base polygons. Okay, now I'm going to, let me go to page 3 now. And I'll keep part of this lower part of page 2 there. All right. So let's make a blow up. Okay, and here's the actual curve. So give that a little bit of curve. And I'm talking about this part right here. It's curving. But you know, in this picture here, it looks like a straight line segment, doesn't it? For that small width, calling it a straight line segment is not bad. But if you focus in on it, it's going to have a little bit of curve. Now here's the left-hand side of the distance polygon. Oh, did I say polygon? Yes. But now a polygon usually has a straight side. So here's what you do. You connect this with this, and there is your polygon. Actually, let me make that a dotted line. See if you can make that a dotted line. Okay, so the dotted line polygon is what we calculate. And we do it a zillion times, every 1/10 of a second. And that is how we get a precise estimate. When you do it 20 times, every 1/10 of a second. And in 2 seconds, you'll know pretty well what your position is to a very good approximation. So, let me see if I can copy that. So here's your polygon. What kind of polygon is that called? It's a trapezoid. All right. And hey, you guys, if you think about it, any trapezoid of this kind can be divided into ching, a triangle and a rectangle. A little bit of V of t and a little bit of 1/2 AT squared. And that's what they're doing. They're computing a zillion narrow distance triangles and the same number, zillion distance rectangles, and then they add them all up. Put this over here. All the triangles and all the zillion rectangles to get position at any time you need. All right? And that's how they do it. Except for one more thing. For NASA, here's the width of this polygon here is delta t. All right? For NASA, delta t is going to be about 0.001 seconds or even smaller. Because those things in 1,000th of a second, if you're traveling 18,000 miles per hour in 1,000th of a second, you're covering a lot of distance. So that's the key for these guys. And that is what the Hidden Figures, that's what they do. So when you go see the movie, whenever you get to see it, yep, that's what they're doing. And we do it on computer now, but back in those days, yep, they had to do it by hand. All right. Can you switch back to display, please? Homework 2 will activate by 5 p.m. tonight. It'll be due Tuesday. You're dismissed. 11:47. Very good.
My
Hey.
name is Aubrey Adams. I emailed you about
Oh, yeah.
courses.
Are you in now? And
No,
I mailed you
called-
back. I
yeah,
messaged you back.
I called you.
You're in. You're in.
Yeah.
Do you have your computer?
Yes, I do. But it's
Break it
not
out.
coming up.
Dare,
Yeah.
she's actually in our class, but she's not. It's not showing up for her. Can you help her out?
Probably UCF Help Desk, and they sent me a maintenance and they didn't pick up. So.
I didn't go once last semester.